Good morning to some of you and good afternoon to others of you. And very welcome to this Axiometric Solutions webinar. Today's subject is measurement microphone calibration. My name is Ole Teilgaard. I'm Director for Global Support and Applications at two of the brands in the Axiometric Solution group. Actually, the brand Audio Precision and Grass Sound and Vibration. We will start as we have a huge program here this morning. So today's agenda is, first of all, we will have a short introduction to calibration. We will have a little discussion about what is an acoustical calibration. We will have a discussion about quality in measurement. How often must I calibrate? Why do we need to calibrate? And we will also have a look at the calibration pyramid. When we are talking about measurement microphones, when we are talking about calibrations, then we also have to have a look at the standard for measurement microphones, the IEC 61094, because this standard describes actually how to calibrate, how to do a primary calibration, the high-end calibration of reference instruments. It also describes how to do secondary calibration. Secondary calibration is the calibration of the daily used instrumentation. We are talking, and we will in this webinar actually discuss secondary calibration of the sensitivity of the measurement microphone. We will also discuss about the calibration of the frequency response of a measurement microphone. We will also have a talk about free-field calibration, free-field calibration in a free-field environment. We will also have a short introduction or discussion about low-frequency calibration, how to do that. And after we have been through most of this presentation, then I will give a short demonstration of the sound of the Grass microphone calibration system. And after that, we should have some time for questions. For questions, in the Q&A function of this webinar, in the right corner of your screen, you can actually find the Q&A function where you can actually type in your questions. Introduction to calibration. For making a documented, traceable, and approved measurement, need your measurement equipment actually to be calibrated. Calibration is a method to establish a relationship between a measuring device and its measurement units. This is done by comparing the device or a device or an output of an instrument to a standard with a known characteristic. You can see we have a ruler here on the slide. And if we would like to calibrate this ruler, then we will actually either use a very accurate ruler, and then we will verify and compare our ruler up against this very accurate ruler. If we are doing it on an calibration lab. And then on the calibration lab, they will use light for a light measurement for doing the calibration of the roller. What is an acoustical calibration? Yeah, calibration, it means actually a comparison of a value indicated by a measurement instrument with a nominal value that is provided by a given standard. The equipment used for calibration must itself be suitable calibration to ensure an unbroken trace back to the standard kept at a national or an international institute. For performing a quality measurement, must we actually have the factors coming up here in a while in mind? First of all, the resolution. Does the instrument meet the requirements for the applications? Do we have enough digits to measure whatever we would like to measure? Accuracy. Does the measurement reflect the true characteristics of what is measured? Precision. Do you get the same result each time you measure the same quantity? The accuracy of a calibration needed is directly depending on these considerations. Why should I calibrate? This is actually a question we receive very, very often. And it is actually not that easy to answer because it depends actually on the type of measurements you would like to perform. It depends also of your quality assurance system. But I can actually give you a few guidelines. First of all, I think it's a good idea to, when you receive a new instrument, to do a calibration or to do what I will call a verification in your measurement chain. So if you receive a new microphone, then you install the microphone in your measurement setup, and then you do a verification, ensure that the microphone will give the right result on your measurement device, analyzer, whatever you are using. When a specific period of time has elapsed, it often we recommend that you do a calibration once a year for a microphone. When a specific period of uses, operation hours has elapsed, it could be in your quality system that you say after 1,000 working hours, then we need a calibration of the device. When an instrument has been exposed for extreme environmental changes, such as temperature, humidity, static pressure, that might have affected its performance, then it's a good idea to perform a calibration. When an instrument has been subjected for shock or vibration, and this might have affected its performance, then it's also a good idea to perform a calibration. Whenever an instrument or whenever the measurement results appear to be questionable, every time we can set a question to what we have measured, then it might be a good idea to do a calibration or at least a verification of the entire measurement chain. Why calibration? Yeah, first of all, it could be because we would like to fulfill externally requirements. It could be legal requirements. It could be requirements written in a standard. It could be because we would like to fulfill internally policies, the company's quality assurance policy, or other internally described policies. Or, and maybe more important, if we are in doubt if we are doing correct measurements. So calibration will actually give us confidence in our measurements. If we look at the calibration pyramid, then in the bottom of the pyramid, we have the daily use instruments. It's actually all the microphones or the analyzer, whatever you are using. Most of you are using daily for doing measurements. These are the working instruments. These instruments will, from time to time, maybe once a year, depending on your quality system, be sent in for calibration. Then you can select or have a traceable calibration. So it is traceable back to a national or international institute or standard. You can also have a level higher with an accredited calibration. An accredited calibration is a calibration performed according to a certain standard, normally the standard, the ISO 17025. You could also have or refer to a reference standard, so it's more a secondary calibration. It's still an accredited calibration, but there's a more accuracy in what is have been done. And in the end, we have the national or international standard, the primary calibration, where we are comparing the different calibration laboratories, so we all are sure that 1 volt is 1 volt in Europe or in US, all over the world. And this pyramid will actually give us the traceability from our working instrument back to a national institute. So we are sure that 1 volt measured with our equipment is also really 1 volt, for instance. The standard for measurement microphone, the IEC 61094. This standard consists of 8 sections or chapters, whatever we call it. Chapter 1 describes specifications, and it is actually specifications for reference microphones, for laboratory reference microphones. So it's actually the microphones described in this standards that are used in a primary laboratory to do calibration of microphones. So this is our reference equipment we have in part 1 described. Part 2 and 3, they describe actually how to do calibration of the laboratory reference microphones. Pressure calibration and free fill calibration. IEC 61094-4 is the specifications for a working standard microphone. It's actually the microphone most of you have on your table. It's the microphone most of you are using every day. The specification for this type of microphone are actually described in this part of the measurement microphone standard. In part 5 of the measurement microphone standard is actually a description how to do calibration, how to do pressure calibration or sensitivity calibration of a working standard microphone. While part 6 describes how to do frequency response check and calibration of a working standard measurement microphone. Part 7 describes the difference between free fill and the pressure sensitivity of laboratory microphones, while part 8 describes a method for doing free fill calibrations of working standard microphones by a comparison method. In this webinar and today we will concentrate us about the working standard microphone, so we will mostly look at the part 5 and 6 as well as part 8 in the standard. If we have a closer look to part 1 and to part 4 of the standard, actually the specifications, then they look like each other. In the specification in the standard, that's described that the microphone should have a certain sensitivity. The microphone, depending on size, should have a certain frequency response. The dynamic range is also described. The size of the microphone is described. It's the mechanical size. Environmental parameters such as static pressure, temperature, and humidity is also described. The influence of these parameters are actually described in the standard. Also, stability is described, both long-term stability, how accurate, how much drift do we actually see over time of the microphone. The short-term stability, how fast is the microphone up, running and measuring correct after you have switched on power to the microphone. If we look at the laboratory part of the standard, the part 1, LS means laboratory, and 2 means it's a half-inch microphone, and P is the type of the microphone. Is it a pressure? P for pressure, F for free fill, and R for random incident microphone. Laboratory reference microphone like the GRASS 40 AU, and if you would like to make a reference microphone, then you have to fulfill all these parameters written in the standard. If we do the same for a working standard microphone, WS for working standard, 1 for 1-inch microphone, P again for pressure, 2 for half-inch microphone, F for free fill, and D for diffuse fill. 3 for 1/4-inch microphones. So it is actually all our working microphones. It's all the microphones we are using daily. And the standard is actually covering 1-inch, half-inch, and 1/4-inch microphones. 1/8 of an inch of a microphone is actually not described in the measurement microphone standards, but all 1/8 of an inch microphones on the market, they are actually made so you actually have the same parameter and data for a 1/8 of an inch microphone as well. Okay, we will have a short look at part 2, 3, and 7 of the standard. Actually, the part describing the primary calibration, and it is actually the IEC 61094-2 primary methods for pressure calibration, reciprocity calibration of a microphone. The principle in that calibration method is that you have a reference microphone, you have a microphone under test, and you have a sound source. This sound source could be a microphone. It could also be a little speaker. But these two microphones are placed very, very close to each other. And then you will actually measure the transfer function between these two microphones. So first you will use one microphone as a source and then measure the transfer function to the other microphone, and then you will do the other way around. And then in the end, you will do calculations for finding the sensitivity of that microphone, the sensitivity of the frequency you have used for doing the calibration. So with this method, you are actually able to calibrate from approximately 20 Hertz up to about 20 kilohertz and do normally not a frequency sweep, but actually do single measurements. So this method is actually a very time-consuming method and normally also rather expensive to carry out. We can actually do exactly the same in a free fill environment. The principle is exactly the same. So we have the two microphones pointing at each other, and then we will use one microphone as a source and the other one as a receiver, and then we will do it the other way around and then calculate the sensitivity at the frequency we are testing for the time being. And it is a method which is mainly used in primary calibration laboratories because, as I mentioned before, it is rather time-consuming process. The IEC 61094-7 describes actually the values when you have done a calibration of a laboratory microphone with according to part 2 and part 3, then there are some way of doing some calculations and actually find the difference and actually find some correction values, and all these are described in part 7 of the standard. If we look at working microphones, then we are going to look at part 5. And the first we will actually look at is actually the pressure calibration comparison. And the principle is that you have a reference microphone, you have the microphone on the test, and then you have a sound source. So these two microphones will see exactly the same. If you know the exact sensitivity of your reference microphone, then you can easily find the sensitivity of your microphone under test. And that's actually the principle. So the principle is with the comparison method that you have the reference microphone, you have the microphone under test, and they are tested either simultaneously or you can do it sequentially, and they must be, of course, exposed for exactly the same sound pressure level. So we can compare with a reference microphone, or we can also do a comparison via a piston phone or a calibrator. If we have a closer look at the piston phone and the calibrator, then we have actually a system like this. We can either use a microphone as a sound source, so the two microphones, the reference microphone and the microphone on the test, will see exactly the same sound pressure levels. If we do it with a microphone as a sound source, then we are able to test or calibrate from about 20 Hertz to 20K, and we will have levels around 100 dB in the little cavity, in the little volume we have between the two microphones under test. We can also have a coupler with a speaker as a sound source. The principle is the same. We can calibrate from approximately 250 Hertz up to about 16K, level up from 70 to 110 dB in this neighborhood. Most of the secondary laboratories, they are actually using a piston phone for doing the calibration. With a piston phone, you do have a volume. It's the one we have here. And then we have two pistons, and these two pistons, they will actually move. They will move due to there's a little motor making them moving. And when they move up and down, then the pressure inside the chamber here will actually be built up. So you will have a certain pressure inside the chamber. This is a fixed frequency, normally 250 Hertz. A fixed level, 94 dB, 114 dB, or 134 dB in this neighborhood. We will have a closer look at the piston phone because, as I mentioned, most of the laboratories, they would actually use a piston phone for the level calibration. The piston phone is a very, very precise sound source. It is based on volume displacement. As we talked about before, we have these two pistons that will build up the pressure inside the chamber. With the piston phone, then we actually have to have one thing in mind. We have to it had to be geometrically controlled because it's the pressure inside will actually be we had to compensate for the static pressure we have. And the frequency 250 Hertz, many piston phones are actually calibrated very, very precise to give us a frequency of 251.2 Hertz. And that's actually due to it's the really center frequency of a 1/3 octave filter. Very precise level. Many piston phone gives 114 dB, which is equal to 10 Pascal. Let's have a little look, because what is actually the difference between a sound level calibrator and a piston phone? Let's have a look at the sound level calibrator 42AG from Grass. The sound calibrator, the principle in a sound calibrator is that we have a little speaker creating the sound inside the little coupler. And of course, there's an oscillator. And to ensure that we have the right sound pressure level inside the coupler, then we have a feedback loop. So we have a pressure sensor sitting here in the coupler, and this pressure sensor will actually measure the pressure inside the coupler and make a regulation of the level to the loudspeaker, so we will actually have the right level inside the coupler. We will also compensate for the static pressure, so it's a part of the regulation feedback. Sound level calibrator is a high precision, or the 42AG is a high precision, multifunction, and easy to use sound calibrator. It conforms with the standards for sound calibrator, the IEC 16942, 2003, and actually also the newest part of the standard, 2018. With the 42AG, you have actually two frequencies. You have 250 Hertz and you have 1 kilohertz. 250 Hertz is a good frequency because all microphones has actually a very, very linear response around 250 Hertz. 1 kilohertz is also another good frequency, especially if you are measuring or using the sound calibrator together with a sound level meter with an A filter inside, where you actually have 0 dB at 1 kK. We also have dual level, so we actually have the possibility for making a linearity check of our measurement chain. As a bonus, then we will also have possibility for looking at the environmental data. So there's also built in a static pressure meter, temperature, and humidity. So we are measuring all three environmental parameters. If we look at a sound level calibrator versus a piston phone, then the sound level calibrator is for verifying our measurement chain. So it is a verifying instrument. I will not call it a calibration instrument, but a verifying instrument for verifying the complete measurement chain. The sound level calibrator is for field use. We can use it outside, inside, we can use it everywhere. We can use it in the field. We can use it with all standard measurement microphones. We can also use it with low noise microphone because we have the 94 dB and low noise microphone. They are normally not measuring more than 110 dB. So it's a little bit difficult to use a calibrator with a higher sound pressure level. We don't need to do any corrections for the static pressure because we have the correction built into the calibrator. We don't need to do any corrections of the microphone's front volume. We need to do a little correction when we are measuring half-inch free-flow microphones, because with a calibrator we are doing a pressure measurement, a pressure calibration, and a free-flow microphone is actually about 0.15 dB down at 1 kilohertz. So it's only at 1 kilohertz we have to do these corrections. If we look at the piston phone, The piston phones are for calibrations of microphones and microphone sets. It's a laboratory instrument. So it's an instrument we have to use in a laboratory. It is very precise and accurate instrument. When it leaves the factory, the glass factory, then we will have an uncertainty on 0.08 dB. You can also have an extra accredited calibration, and it will give you a even higher or less uncertainty. You have, of course, with a piston phone to correct for the static pressure. You also have to correct for the front volume of the microphone. So it is a little bit more difficult to use a piston phone than to use a sound level calibrator. And it's also the reason why a sound level calibrator is for daily use, and it is for verification to ensure that the whole measurement chain are measuring correct. So the sound level calibrator is not for secondary calibration laboratories, but it's only for daily verification, while the piston phone is a laboratory instrument for secondary calibrations laboratories. Let's see what we actually are doing when we are making microphone calibrations. When we are making microphone calibrations and looking at the microphone sensitivity, then in the standard it is actually described that, and it's only described for the microphone capsule. The microphone capsule is only this one here. And it is actually described as an open circuit sensitivity. And it means that's actually the sensitivity for the microphone capsule without the load from a preamplifier. So we are not looking at the preamplifier gain, we are only looking at the microphone. Closed circuit sensitivity is actually the sensitivity we will measure on the output of the preamplifier. So it is actually the sensitivity for both the microphone and the preamplifier. If we look at it, then the microphone has a certain capacity, CM, and if you look at the input of our preamplifier, then we can actually see there's a little capacitor here in our preamplifier. So that's an input capacitor of the preamplifier, and we will actually have a voltage division between these two capacitors. So the output of the preamplifier is a little bit less than the my output of the microphone is. And yeah, it can actually be calculated. It can be calculated according to this formula, and then we actually will have the damping or the attenuations in dB. It is in neighborhood for a standard half-inch microphone mounted on a half-inch preamplifier. It is in the neighborhood of 0.2 dB in this neighborhood. Open circuit sensitivity. We talked about it before. It's only for the microphone. It's independent of the preamplifier. It's a standardized value, but it's actually not a practical value because all of you will actually use a microphone together with a preamplifier. So therefore, you from day to day, you are actually using the closed circuit sensitivity, which of course depends on the preamplifier. And it is not a microphone parameter according to the IEC standard. But yeah, it is a very, very practical value because it's a value you can put into your analyzer, so you are ensured that you are measuring correct. How to measure the open circuit sensitivity. It is actually done in 2 steps. First of all, we will actually mount our microphone on the test, only the microphone capsule on the test, on a preamplifier, and this is actually a special preamplifier. It is called a insert voltage preamplifier. When we will mount it on this preamplifier, and then we will actually mount the microphone inside our piston phone, because with the piston phone, then we know exactly the pressure we have from the piston phone. So we will actually start measuring the output of the microphone, and of course the preamplifier, and it is actually equal to VO. Next step, then we will actually switch off our piston phone, and then via our voltage insert preamplifier, then we will actually have a generator signal with a certain level. This generator will have exactly the same frequency as the piston phone, 250 Hertz. And then we will actually now start making a regulations of the level of our generator. So we will adjust the level of the generator until we, on the output of the preamplifier V2, measure exactly the same as we measured before when we had the piston phone on. When we have done this, then we will actually measure the output voltage of our generator, because the output voltage of our generator is actually equal to the open circuit sensitivity of the microphone. So for measuring the open circuit sensitivity, we are using a insert voltage preamplifier, and then we are doing it in these 2 steps. Step 1, where we are measuring with our piston phone, and then we switch off the piston phone, and then we connect our generator at the same frequency, adjust the level of the generator until we have the same output as we had with the piston phone measurements, and then we measure the generator level. A typical setup is a setup like this, where we have an analyzer, a power module, supporting insert voltage, and of course an insert voltage preamplifier. Then we can actually do the measurement. When we are doing calibration, then we have to remember that our piston phone level must be corrected for, first of all, it must be corrected for the static pressure. So we have to look at today's static pressure, and then do a correction for that. We also have to correct our piston phone from the front volume of the microphone. And yeah, in the end, we will end up with the piston phone level, or the level the piston phone is giving us, LC. The microphone sensitivity, when we measure the microphone sensitivity, then it must actually be measured in millivolt per Pascal, and also in dB relative to 1 volt per Pascal. So yeah, normally we are measuring in millivolt, so we can actually calculate it sensitivity directly in millivolt, and we can also do the calculations into 1 volt per Pascal. So we need to have both values on the calibration chart. When we are doing calibrations, then we also have to have to take uncertainty into considerations. If we look for an example here for a 1-inch or a 1/2-inch microphone, then the uncertainty chain, when we're talking about sensitivity, could actually look like this. We have our reference microphone where we have a certain uncertainty. We have distortion of the microphone. We have piston phone stability. We have temperature deviation. We have static pressure corrections. We have humidity deviation, and we also have tolerances in our analyzer or voltmeter, whatever we are using for doing the final measurement. So we actually have to take all these uncertainty into consideration, and it will give us a totally deviation where we have the uncertainty 1 multiplied by a rating, how important is it, and then in the second power, and then we actually have to do it for all the uncertainties we have in our chain, and then do the calculations. And in the end, we will end up with an expanded uncertainty, normally with a K factor equal to 2, like it is here, where we are looking level calibration at 250 Hertz. We have the reference microphone, distortion, and things like that, and then the rating, and in the end, we can actually calculate the totally uncertainty budget for that measurement. Part 6, it describes the measurement microphone calibration, the frequency response by use of an electrostatic actuator. When we're using an electrostatic actuator, we need, of course, a generator able to do a frequency sweep in the range of interest. We need an electrostatic amplifier able to give us a very high output voltage, and we need the electrostatic actuator itself. Let's have a closer look. If we look at the principle of a typical setup of a measurement for a measurement like this, then we actually have our analyzer. The output of the analyzer will go directly to our electrostatic amplifier, an AC amplifier, and inside the amplifier we will have a high DC voltage, normally 800 volts. So on the top of our electrostatic actuator, we will have this 800 volt DC plus our excitation signal, the 70 volt RMS signal. Then we have the microphone and the preamplifier going back to our analyzer. In the electrostatic actuator, we will build up an electrostatic field, and our excitation voltage will actually make the diaphragm of the microphone moving. So it's a constant force we will have on the diaphragm. Let's have a closer look on how it works. See the plate we have in our actuator, the one here with the holes, it will together with the diaphragm of our microphone actually be a condenser, a capacitor. So we have these two parallel plates making a capacitor, and between these two plates we will actually build up a force which actually will make the diaphragm moving. The force or pressure, it is frequency independent, as long as the applied AC and DC voltage are kept constant. That's a formula how to do the calibration or find the pressure. And if we do these calculations, then with a 70 volt AC and 800 volt DC, then we will have approximately 1.4 Pascal sound level on our microphone when we are doing this actuator calibration. The actuator calibration can be used in a very large frequency range from 20, 100 Hertz up to 200 kilohertz. When I say 20, then it's actually due to the standard tells us that you can use the actuator methods from about 10 times the low frequency cutoff of your microphone, the 3 dB point of the microphone. It will give, in some, depending on type of microphone, half-inch microphone, then you will be able to measure down to 20 Hertz. For 1/8 of an inch or 1/4 inch microphones, it's a little bit higher up in frequency you have to go. The pressure the actuator produce on the microphone diaphragm is frequency independently, as we saw before. If we keep the AC voltage and the DC voltage constant. But when the diaphragm is moving and you have this plate, the actuator, on top of it, then there will be a certain resistance between the actuator and the diaphragm itself. So it will at higher frequencies give a little deviation. So you actually have to make a little compensation even for a pressure microphone. But this compensation is actually a very, very small compensation in the neighborhood of maximum 0.2 dB. And as the uncertainty for an actuator, electrostatic actuator principle is, you would normally have an uncertainty of 0.4, 0.5 dB, depending on, again, the frequencies. So normally you will consider the obtained level as actually the pressure level the microphone can is measured, have measured. So the actuator will give us a pressure measurement, and it means that, of course, when we are measuring free-field microphones as well as random incidence microphones, then we have to do a compensation for finding out how the microphone actually will act in a really free-field environment or a really random incidence microphone environment. So we have to add the free-field and random incidence or diffuse field corrections to our pressure measurements. If we look at low frequency limitations, as I mentioned before, the electrostatic actuator can be used down to approximately 5 to 10 times the lower limit frequency cutoff of the microphone. This is actually due to the electrostatic method will not excite the venting system of the microphone capsule, which at lower frequency can be seen as a reduction of the totally stiffness of the microphone capsule, and therefore will the microphone capsule be more sensitive at lower frequency if an actuator is used. I will try to show it here. The green curve here is actually the actual roll-off of a microphone set. So this is the really roll-off. While the blue curve, the blue curve we have here is actually the roll-off of the microphone when the microphone is measured with an electrostatic actuator and a electrostatic amplifier. Theoretically is the dotted curve if we measure it on with an actuator, but the light blue curve is actually due to the cutoff of the electrostatic amplifier itself. So normally, if we are measuring, or if we could measure with an actuator the low frequency response, then it will be more or less a flat line, while if we measure under the right conditions, then we will measure correctly and we will see the right roll-off like the green curve. Also for frequency response, when you are using an actuator, then we have an uncertainty budget, and the principle is exactly the same as we saw before. We have the complete chain, and we have to take all the parts in that chain into consideration, and we have to weight them, and in the end we will have a totally value for them, and then we are able to calibrate the expanded uncertainty K equal to 2. If we look at the methods for free float calibration of according to the working standard, then it's actually a comparison method. So we have a setup like the one we have here, where we have a reference microphone and we have a microphone under test. We have a sound source, and we are using normally an anechoic chamber. There are actually two methods. We can either use, as mentioned here, an anechoic chamber or a free float chamber, or we can use a time selective techniques. Let's have a closer look, because in both cases we will actually need a sound source, and the sound source can either be a speaker or a microphone. We need also a reference microphone with a very well-known free float response. A reference microphone may be measured according to the primary standard, and of course we need the microphone on the test. And what are we going to do? First, we will measure the free float response of our reference microphone. Then we will measure the response for our microphone on the test, and we have to ensure that we are placing the microphone in exactly the same position as we have placed the microphone. So we had to ensure that these microphones have exactly the same acoustical field and the same acoustical impedance. Then we measure the response of the device on the test, and we are actually assuming that the acoustical sensor for the two microphones is at the same point, and that the sound field remains the same. And then we can actually find the free field response of the device under test, and it is actually the difference between the two microphones. If we look at the time selective techniques, then it's actually more or less the same. We are using exactly the same, more or less the same setup. But what we can actually do it in a living room, in a standard room. So what we actually are doing with our analyzer is that we will send an impulse to our sound source, and this impulse, when we are doing measurements, then we will actually in the time domain we will remove the reflections, and in the end we are able to see our response from our microphone. And then of course we had to do the same calculations as before. First we had to do this the measurements, the setup for our reference microphone, and then afterwards we had to do it for the device under test, and then we had to calculate the free field response for the device under test. Typical setup here for the time selective techniques. Our audio analyzer, for free field measure in a free field chamber, frequency response measurement. For the time selective techniques, acoustical response measurements, including time selective functions. Low frequency calibrations. As mentioned before, if we would like to measure the low frequency cutoff of a microphone and calibrate the low frequency cutoff of a microphone, then we have some issues with the electrostatic methods, with the actuator methods, because we would actually measure wrong. We can, instead of the electrostatic actuator, actually use a piston phone principle, or a principle in a piston phone, and it could actually be, and that's actually what we are doing in the glass low frequency calibrator, the 42AE. In this one, we actually have an amplifier, we have a speaker, we have a coupler where we have mounted our microphone inside this coupler. If we look at this at a speaker, then the speaker, it consists of a coil where we have a certain length. It consists of a magnetic field, and when we connect it to the amplifier, then we will have a current going through the coil, and by the magnetic field, the current, and the length of the coil, then we can actually calculate the force. And actually, when we have the force is actually equal to the pressure the speaker is able to give us inside our coupler. With the force, we can, if we measure the current, then we can also have an idea of what the force or the pressure is inside the little chamber. That's actually the principle in a chamber like this. When we are doing low frequency calibration, then it's very, very important that that the venting system of the microphone is venting into the coupler, the whole coupler, because otherwise we will just measure the difference between the pressure inside the coupler and the pressure we have outside the coupler, and that's actually not the idea. This method can be used for microphone calibrations or of microphone capsules. It is of course recommended to use a preamplifier with an extra high input impedance, actually to avoid a conflict between the acoustical and electrical cutoff. The acoustical cutoff is the cutoff done by the venting system, while the electrical cutoff is the cutoff done by the preamplifier itself. If we look at an overview of calibration equipment, then we have the Grass 42 AG multifunctions sound level calibrator. It's more it's for sensitivity calibrations, and it's more for verifying your whole measurement chain. We have the piston phones 42AA, AP, AC for sensitivity calibration, for laboratory calibration. 51AB is a phase calibrator. It's a 2-port calibrator. It can actually be used for sensitivity calibration. It can be used for phase calibrations of a sound intensity microphone, but it can also be used for frequency calibration up to about 16 kilohertz for a standard microphone, where you have a reference microphone in one port and the device under test in the other port. Then we have the low frequency calibrator, only for microphone capsule, where we can make the low frequency sensitivity and low frequency sweep. Electrostatic actuator for frequency calibration, an electrostatic actuator for frequency calibration, and then we do also have our microphone calibration systems, which are able to calibrate microphone sets as well as preamplifiers, and it's both sensitivity and frequency calibrations. And I can actually see that I have spent 7 minutes more than expected, and I have now a demo, a demonstration, but for the one of our microphone calibration system. But for the one of you who doesn't have time for that, then I will say thank you for participating in this webinar. And else I will actually go through the microphone calibration system. See, when we start the microphone calibration system, then as all other systems, we have to put in and we have to tell the system who is the user. The system will actually automatically from the piston phone read the barometric pressure. So we put in the reference conditions, we will put in the temperature, and we will also put in the humidity. When this is done, then we are actually ready to start a calibration. So we can click on the new calibration button, and then we will have a page coming up like this, where we actually have a list of all the microphones we are actually able to calibrate. We have microphones, we have microphone sets. We do also have something called random combinations, where you might have a microphone and you might have another type of amplifier that normally used together with that microphone, and then you can actually combine these two together and do a calibration. See, I have a microphone capsule, actually a 40 AG microphone capsule here in front of me, so I will use that one and do the calibration of that one. I will start putting in the serial number for my microphone. It's done there. Then I can put in, I already done it, I can put in who's the calibration ID, the customer, an ID number, customer number. I also have to tell the system at which frequency I will actually start. I would like to start from 20 hertz. So that is done. See, now we can actually see we have the test conditions into the systems. We also have all the data for the microphone we are going to calibrate. Then we actually have two level calibrations. We have one called level calibration. Itself is actually the reference where we are using a piston phone. Level calibration 2 is where you can use a sound calibrator if you would like to have a level calibration, let's say at 1 kilohertz. But in this case, I will do my calibration with my piston phone at 250 hertz. So I will start the picture. When I start the picture, then start the measurement up, then the piston phone will start automatically, and we can actually see that now the pressure is built up inside the little chamber, and the microphone starts to be to have the right sensitivity. See, we have two curves here. We have a white curve and we have a red curve. The white curve is an instantaneous curve, while the red curve is an average curve. See, I just made a little knock in the table, and you can actually see that the microphone could hear that. So the instantaneous curve went very, very high, and the average a little bit higher. The stabilization light is green, and we will wait a little. Normally, I will wait about half a minute to ensure that everything is okay. There was actually the first part of the calibration. It was the piston phone part. And now we have switched off the piston phone. We have switched on the generator. And we have now done the voltage insert calibration, and we have calibrated the open circuit sensitivity for our microphone capsule. And we can actually see that we have at 250 hertz, we have the sensitivity in millivolt, 14.47. We have it in sensitivity in dB relative to 1 volt per Pascal, minus 39.79, and we have actually a deviation from the nominal sensitivity. So this microphone here is a little bit more sensitive than what we normally have for this type of microphone. The next we actually have to do is a frequency calibration. So we press the button, and we will press the start button, and we can see now we have started it up. We can see that the test frequency is stepping up. We are actually stepping with 1/6 of an octave standard in our system. We are measuring from 20 hertz to 40k, and yeah, we can see that the response is not okay. We don't have any green indication, so we will run it again, and now it looks actually much better. But I can see we still have some issues at the low frequency, and we also have a little issue at the higher frequency. The issue at the low frequency is actually due to I have forgotten that we have a 20 hertz low pass filter in our power module. So I have now switched this off, and we can see that we are measuring very, very flat from 20 hertz and up. We still have a little issue and in the top. And yeah, to be right honest, it's actually due to the microphone I have here is my demo microphone. And yeah, it's touching the tolerance, but I will accept it. And if we look now, then we did have our sensitivity with a green indication, everything is okay there. But we have also done the frequency response, but it's failed the frequency response. So now I can save my data, and it's what I call the raw data. It's all the measured values, and if I press on the print PDF, then it will actually create a certificate, a nice certificate, and then we can use that. It was actually the calibration, but let's have a little look at the results. So we have the results here where we have the microphone. That's one measurement. Here, if I press this one here, then I can actually see the frequency response of our measurements. I also have, if I press the sensitivity, the possibility for see how is the sensitivity. If we have made many calibrations of these microphones, then I will actually be able to see all the different calibrations, and I could actually compare these and see if the microphone has drifted over time. If we look at the microphone definitions, then it's actually here we can see all the test data we have used, or the fundamental test data we have used for doing this calibration of the microphone. So that's data for our coupler, there are data for our second piston phone or second level calibrator, if we have such one in for our system. There are the data for the microphone itself, name of the microphone, size of the microphone, type of the microphone. Is this a pressure type, free flow type, etc. Also polarization voltage. We can also see where do we actually store the data, where do we store raw data, where do we store the certificate, where do we get the templates from the certificate. We do also have data for the sensitivity tolerances, upper and lower tolerances, both for sensitivity 1 and 2, and the same for our frequency sweep. And under equipment, we can actually see the list of equipment we have used for doing this calibration. Okay, it was about the microphone calibration system. And I will actually go back to the presentation and actually to questions. As mentioned in the beginning, if you have questions, then please use the chat function. And I will now go and see what's in the chat functions. For the one of you who would like to say, we have heard what we would like to hear for today, then I will say thank you. Thank you for participating, and hope to see you at one of our next webinars. I don't think there's any questions. Oh, yeah, that's one. There's one asking. Here it is. One is actually asking if there's any special consideration for a 1/8 inch microphone when doing calibration of that. No, actually not. For sensitivity calibration, you need, of course, to have an adapter for your piston phone, so it will fit into your piston phone. For the frequency part of it, when you buy an electrostatic actuator from Glass, the RA0014, then an adapter for a 1/8 inch microphone is actually included. Of course, the level of a 1/8 inch microphone is very small because the 1/8 inch microphone has a very low sensitivity, so you might have some noise, electrical noise, background noise in your room, which you have to take into consideration, but else it is actually straightforward. Then we have one here. How is the traceability for the test platform performed? When we are selling our 90CA-S2 system, then we will normally sell it together with an accredited calibration. So you have actually a traceability back to a lab here in Denmark. So when we are selling it, then it is actually traceable to DFM, which is the highest authority of calibration in Denmark. So it's a primary lab you have the traceability back to. Do you have any statistics on how long calibration stays valid from a practical perspective? No, actually not. And it depends on how you are using your microphone. I will say, if you aren't using your microphone, or your microphone is kept in a laboratory where you have a constant temperature, constant humidity, and things like that, then the microphone won't change anything over time. It's in milli dB you will see changes. But if you're using the microphone in the field under different temperatures, different humidities and things like that, if you also are dropping the microphone from time to time, then you will see changes in the sensitivity and also in the frequency response. So it's difficult to say. Any warm-up time needed before starting and using an electrostatic actuator or analyzer? Yes, there is a warm-up time. We recommend a half an hour when you have to switch on your system, and half an hour before you would like to use it. The microphone itself do also have a warm-up time, especially external polarized microphone where you have the 200 volt polarization voltage, it will actually take, there's a time constant in the microphone, which actually takes some time before the microphone actually build up the pressure. So yeah, that's something you have to have in mind. But standard half an hour, and when you put on power to an externally polarized microphone, then you have to wait a minute or so before you actually do the calibration. There's one who's asking if I have a sound level meter, a calibrated sound level meter, should I still have a calibrated sound level calibrator to perform daily check? I would actually recommend it, and the reason why is if you only have your calibrated sound level meter, then it's calibrated maybe once a year, then you don't know what's actually what is actually happening with your sound level meter as well as your microphone you have mounted on your sound level meter over time. So therefore, I think it is actually a good idea to have a calibrator to know where you actually are. And yeah, I would also recommend that you have a yearly check of the sound calibrator. Oh, that's okay. When we talked about before, then about statistics of short of a long-term performance. It's actually said here that it's for outdoor applications. Let me see the questions again. For outdoor applications, when you are using a microphone in an outdoor environment, then the calibration will be valid also over a long period of time. Of course, the microphone is actually sensitive for humidity, is sensitive for temperature, and also for static pressure. So you actually have to take these parameters into consideration. But else, with a microphone, an outdoor microphone, we would actually recommend that there's a built-in remote check of the microphone, so you can make a daily verification of the microphone or the whole measurement chain to ensure that you are measuring the same as you actually did yesterday when you made this verification. There's one here from experience. Don't mix 250 hertz and 1 kilohertz meters. Decide which best suit your measurement and choose 1 meters for all of your microphone. And it is actually a very good idea. In many cases, as I mentioned, then I would like to use a piston phone for my laboratory calibration, and I would normally use a level calibrator for the daily verification, the daily check, whatever we call it. And when we are using the calibrator, then it's actually a good idea maybe to use 1 kilohertz, because then if you one day are using an A filter or another kind of filter, then maybe you don't have to take anything in to take the damping you have between 1 kilo and 250 hertz into consideration. So it is actually a good idea. I think if you use the calibrator and use it in the field, then use it at 1 kilohertz. And then there's one asking here, where can I calibrate the environmental part of the 42 AG? We can verify and calibrate it here at GRASS. I think it was all the questions. So I will wait 2 minutes if there are coming more questions, and then we will stop. Okay, I don't think there are any more questions. I do hope I have answered all of them. Once again, I will thank you for participating in this webinar. And yeah, hope to see you soon, and some of the other webinars we are providing. So thank you, and thank you for today, and I wish you a very nice day.